So sometimes when we're doing node analysis, we may find that we have some difficulty in applying the rules, the steps that we talked about. So specifically, we're going to find a problem when we have a floating voltage source. And so we're going to walk through what problem arises and then how to overcome that. So here's our example circuit over here. And we first, number one, we need to find our unknown nodes. And we're going to start with just labeling them. I really recommend drawing the nodes out if you're having trouble figuring out which nodes or how many there are. Like literally bring colored pencils and draw them in. So here's our first node. This is our reference node. So this is voltage equals 0. And so that's not an unknown. We know that one's 0. We also have other ones. Let's draw in the other ones. So we have a V, and they're already conveniently labeled because this problem is given to us, but you would label them as you see fit. So we have one node on the left, we're calling that V1, and we have one node on the right here, we're calling that V2. So you might say, well, what about the voltage sources? What if can't we suppress those, or don't we know them? Okay, well, let's suppress them real quick. And we know that if we suppress the current sources, these will become opens. And if we suppress the voltage source, it will become a short. And so actually, we would just have one unknown, right? And if you think about it, if we know V1, we actually know V2. If we know V2, we know V1. So actually, we're only going to have one unknown here in terms of voltages. Okay, so we can write that down over here. Let's just say that we are looking for V2. I don't know. We're going to say V2. And then we know that V1 from that is going to be directly equal to V2 plus Vs, the source voltage. Okay, so only one unknown. And now we can erase this suppression. This is just to figure out the number of nodes, and after that you can go back and ignore that. Now we would try to apply our Kirchhoff's current law. Sorry, there we go. So great, we just apply KCL at each node. So we would say, well, we're going to start with V2, and we would say, well, let's see what we have. Oops, that's and this is just, I just write this V2 so I know which node I'm looking at. And let's draw this one. And again, I prefer to do currents out of it. So we're going to have 0 equals, here we have I2. That's a independent source, so that value is given. And we would have this current. So this would be V2 minus 0 over R2. And then we have this current going into the current source, but I don't know what that is because remember from the voltage sources to current sources, the voltage source will maintain that voltage, and it can be any current, positive, negative, 0, any current, to make sure that that voltage is met. So I don't know what that current is going to be. We can say, well, let's just do the other side. You know, I'm not gonna write this one down. I'm gonna walk us through mentally here. What if we were to take the other side? So let's we could define our unknown as V1 and then apply KCL on the other side. You'll see we'll run into the same problem because if we were to look at this current, we could define those, but we don't know, again, the current going into the current source. So what can we do here? We can utilize the fact that the current coming in here has to be the same current, the sum of these two going out. Another way to say that is to draw a bigger circle, essentially. Oh no, it's hard to erase all this. Sorry, guys. Okay, it's not beautiful. Okay, so instead of that smaller node, what we're going to do is do a super node. And I'm going to draw the node over the whole thing. And because the current going in and out of the current source, that has to be conserved based on conservation of energy and Kirchhoff's current law. We can instead just do this whole thing here. So actually it's going to be, I'm just going to erase this, call it supernode. Here. Supernode. If we really want to be specific, it'd be V1 and V2. So that's together, so it'll land here. And so then we would do the same thing. So we have I2 coming out, V2 minus 0, and then plus V1 minus 0. I'm going to keep V1. No, actually, I'm not gonna. I'm gonna do substitute this guy in right away. So it would be V1, which is equal to V2 plus Vs. I'll put it in parentheses. Minus 0, so that's this current, divided by R1, and then plus, here it's just negative I1. And all that has to be equal to 0. So you can see, and we'll just make it really clear, our known values are these currents and the voltage source and the resistors. We can see that we have these values are all known, known, and known, and known here. And our only actual unknown, I'll put this in purple, is Vs, so here. And we can see that we have that here and that here. So we have one unknown, one equation. So our last step is to solve the system of equations. Okay, so you solve for V2, and then you have a fully defined system. You know all the voltages, and you can then find any branch current that you need to. So if you end up with a floating voltage source, instead of doing KVL on each side of it, put a supernode around the whole thing, and then look at the currents defined around it. And note that you have to write everything in terms of the unknowns if you want to get your one equation and the X number of unknowns matching X number of equations.